it. Okay, so I have, I'm just do the one, and then I'll give you guys a few minutes to finish up. But I want to know grams of, right, each product. So that actually means I need to, hang on, find a pen. For some reason, my little wheelie thing got messed up. All right. I need to find two answers. Those are the answers I need, right? So starting with grams of aluminum, I want to know grams of aluminum oxide. So I have 4.7 grams of aluminum. What's the first step? Like in all of these problems that when we're going to be using this pathway, grams to moles to grams. And we're starting with grams and we want to end with grams. And so we're going to use the whole thing. The first thing we want to do is convert it to moles. And so for aluminum, the molar mass is what, 26 point, there we go. 26.982 grams of aluminum for every 1 mole of aluminum. And then I need to do my mole-mole conversion. That's this part here, right? And what's the molar ratio of aluminum oxide to aluminum? What's the relationship? Looking at the equation.
1 to 1.
No, from here, this and this, right? I'm going to do the first product, then I'll do the second product. So it's 1 to 2. All right. So it's 1 mole of aluminum oxide for every 2 moles of aluminum, like that. So if you're looking at where we're at, grams of aluminum have canceled, moles of aluminum have canceled, and then I have moles of aluminum oxide. So now what I need to do is go to grams of aluminum oxide, and again, anytime you do one of these conversions, these are the molar mass of whatever you're starting with. So I need the molar mass of aluminum oxide. Somebody calculated that already, I'm assuming? Yep, sounds about right. 101.961 grams for every mole of Al2O3. Then the moles will cancel and I'm left with grams, and that's my answer. Well, that's not my answer. You know, type it in, that's your answer. Having one of those days.
Having one of those years.
Oh. Okay, so I'll do this one just to double check. 4.7 divided by 26.8982 divided by 2 times 101.961. Like 8.88. And that's grams of aluminum oxide. 8.9 Al2O3. So that becomes 8.9 grams Al2O3. Because this number here, 2 sig figs, right? Is that what you get? Those of you who got it? Is that what you got?
Yes.
So that's half of the first answer, right? This is part of the 8 steps, right? It asks for the mass of each product. So there's the first product, and then you have to do the exact same thing for the second product. You'll start, you want grams of iron. And that's going to, starting with 4.7 grams of aluminum.
Thank you.
And this part's exactly the same. And then you need the mole ratio of iron to aluminum. So that's going to be 2 moles of iron for every 2 moles of aluminum. And yes, you could have used 1 to 1. And then I need the molar mass of iron. And then that's 50, what is it, 55.85 or something like that? I don't remember.
5.85.
Oh yeah, 58? Was
No,
it?
55. No, yeah, 55.
It is 55.85, okay. This is random memory stuff. I have a harder time remembering my kids' names when I'm yelling at them. Okay. Start with the oldest name and then work your way down. Oh, she was there and she disappeared. Interesting. Maybe she couldn't hear me. Maybe she wants a video. I don't know. The camera's stupid and it comes upside down. Yeah, it doesn't flip over even though the screen's flipped over. Or it hasn't. Okay, so just a couple of points about this. I know a lot of you have been making a habit of when you calculate the molar mass, you calculate the molar mass for like 2 aluminums. Don't do that. You'll see how these 2 problems look exactly the same until you get to this point here. They can only do that if you only use the mole ratios, like these numbers, the stoichiometric coefficients. If you only use them at this step here, then you could just have the mass of aluminum for the calculation and the mass of the iron or the mass of the aluminum oxide. You don't have to factor in all that other stuff. Right? But yeah, some of you have been doing 2 times, if it says like Al2O3, that's fine. You're good with that one. You write that molar mass. But if it said 2, then you'd be calculating twice that number. Don't do that. Just molar masses of the compounds, and then we take care of the ratios of compounds just in the mole ratios. It's like 2 aluminums to 2 irons, or 2 aluminums to 1 aluminum oxide. All right, I'm not gonna do the next one. You can do the next one. All right, next question. So it says lead ions can be precipitated from a solution with sodium chloride according to the reaction. That's the reaction. When 135.8 grams of sodium chloride are added to a solution containing that many grams of lead, a lead precipitate forms. That's the PbCl2 solid. The precipitate is filtered and dried and found to have a mass of that. Determine the limiting reactant, theoretical yield, and percent yield for the reaction. Okay. Limiting, first part. We're going to find the limiting reactant. Okay. So to do that, you take the mass of each starting material and you convert it to mass of product. Okay. I'll make a little note here. For each reactant, calculate mass of product. So, for example, hey guys, keep it down a little bit. I can't hear you from up here, so I can't imagine. All right, so I want to know I'm going to start with the sodium chloride. So I want to know grams of PbCl2. And then I have 135.8 grams of NaCl. Same thing, grams to moles to moles to grams. Made that line a little long. I don't need quite that long. Okay, so then I need the molar mass of sodium chloride, which is, some of you know? What?
252.4.
For sodium chloride?
58.4.
Yeah, you're thinking about the other one. 58 point.
443.
Yeah, sounds right. And then I want moles of lead. So there's 2 sodium chlorides for every mole of lead chloride. All right. So it's 1 mole of the product. And I'm trying to get rid of the sodium chlorides for every 2 moles of sodium chloride. Like this. And then what? I have moles of lead chloride and they need mass, right? So it's another molar mass. What's the molar mass of that compound?
278.1.
Yeah. Like that. So we're gonna do that calculation, you'll get a number, all right? That takes care of this guy. So now we have to do this one. Again, part of the 8 steps, right? We're doing like, literally like 8 steps. This problem has like 10 steps in it. So we're going to say grams, the next part is to say grams of lead chloride. It looks exactly the same almost, PbCl2. And then I'm going to start with 195.7 grams of lead 2+. Now, the way you do this problem, and this is not something I actually talked about, you just need the mole, because I didn't think about just doing ions. All you need is this number, 207.2. That's the molar mass. The fact that it's a 2+ ion means it lost 2 electrons, right? That's inconsequential relative to that total mass. So you're just going to use, in calculating the moles of ions, we just ignore the fact that it lost the 2 electrons because they don't weigh hardly anything. So we're going to say 207.2 grams for every mole of lead 2+. Now, if you want to calculate like the mass without 2 electrons, then you can just take the mass of 2 electrons and subtract it. And what you'll find out is it's like the same number. So I had a colleague many, many years ago used to give students that problem, and then they got confused when they got the same answer over and over again, and they're like, we don't understand. And then he would yell at them. Nice. So now what do I need? All right. This is grams, moles. I need moles of product. So I need the mole ratio, and it's 2 sodium, 1 lead, sorry, for every 1 lead chloride. So it's a 1-to-1. So it's 1 mole PbCl2 for every 1 mole of lead, 2+. And then we need the mass of the product. So it'll be whatever that is, and that's the 278.1. And you get an answer here.
So 262.7.
This comes out to 262.7.
The bottom one, the top one to and 646.2.
646 point something.
Two.
2. This is PbCl2. PbCl2. Okay. So, how much can you actually make? Can you make 646 or can you make 262? Right, because once you do that, what happens? Yeah, the lead's all gone, right? The lead ion. Basically, you're calculating how much product can be made from this much lead ion. That's how much you can make, all right? What that actually means is once you make this many grams of this product, this has all been used up. It's all in the product. So the limiting reactant is what?
62%.
No, that's actually the theoretical yield. The limiting reactants is what gives you that number.
Oh, the PP2 plus?
Yeah, this is limiting. LR. The theoretical yield is this guy. So like you can't really do one without doing the other. You got to do them at the same time. That's why one of the reasons why these problems are tricky, because they tell you to find the limiting reactant, but you only find it while you find the theoretical. You do both. You're doing both things at the same time when you do it. And then your percent yield. Wait, so what number haven't I used yet? Yeah. And that says, and found to have a mass of, so that's your actual yield. That's how much you actually made, right? So this is actual yield. So the percent yield is the actual yield divided by theoretical yield times 100. So that's going to be,
96.1.
well, yeah, I'm going to write the 252.4 grams divided by 262.7 grams times 100. Yeah, it looks like 96.1, you said?
Yeah.
I'll go with that. Sounds about right. Like that. And the units, grams, you write the units and they cancel out.
You know how in the second part we went from lead, we converted lead over to lead chloride?
Yeah.
And in the first part, we went from sodium chloride to lead.
Yeah.
And I was looking
Lead
at-
chloride.
Oh, okay.
Yeah, you got to go to this. So when you're doing this sort of theoretical yield kind of calculation, when you're given two reactants, you have to take both reactants to the same product, the same point, so that you can compare. Because if I told you on this one how much, if I told you for this number how much lead chloride you could get, and for this number how much sodium ion you could get, you couldn't compare because they have different molar masses. You can't make that comparison. You have to go to the same thing. So apples and apples.
So sodium chloride is like a whole separate compound from lead, right? So,
Yeah.
okay. So like in my mind, I was like trying to convert sodium chloride, and then on the reactant side, it's just sodium with the 2. So you're not converting sodium. Oh,
That's what that's for.
right.
So you just have to remember on either end, it's a gram to mole conversion or a mole to gram conversion. It's either divide by molar mass or multiply by molar mass. And when you're in the mole form, all you use is the mole ratios. All you deal with is the mole ratios in the middle. So like here, right, this is a conversion to moles of sodium chloride. Here, this is the conversion to the moles of lead. So all you're doing in the beginning is converting everything to moles. And actually, a lot of times when people do these, because it can get confusing to do one and then another, they just do them both at the same time. Because they'll set it up top and bottom like this, and they'll say, okay, I have grams, I go to the mole, so they use the molar mass. And then they do the mole conversion, and they'll say moles of lead chloride, that's what they're looking for, and then divide by whatever they started with. So this is the mole ratio to get the moles of chloride, mole ratio to get the moles of lead chloride. And the last step is to convert it over to grams. So then they look up their molar masses and they just multiply by the molar mass. And this is going to be exactly the same because this part's the same. So study the problem in its like the form of the problem, and then just do some more. It'll start to click. But if you just try to do one or two and say, well, that's it, I did my homework, you're going to be like on the test, you're going to be like, what am I calculating? Where does this go? How am I converting? It takes, homework is not studying for the exam. Homework is just getting ready to study for the exam, if that makes sense. And I'm not one of those teachers that wants to give you like, I mean, how would you like to do like 30 of these? Yeah, the drill and kill, I'm not that guy. I'm the, here's the good problem. Do the good problem, study it, do it again, all right? Find more examples until you figured it out. And when you figured it out, stop doing it.
Bless you.
Okay? Good. He's here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is 2. I know the 2. Huh?
We should just practice.
There's more notes over here.
Is this going to be on there too?
No, this is all new stuff. And by the way, this stuff has no calculations in it. Like what? It's all touchy-feely qualitative stuff. Actually, it's not, but there's no calculations. That makes some of you happy. I know. Yeah, pile of homework. Anytime you want that, by the way, what you do is you put a little note on the thing. You have this problem. And I'll work it out. Oh, for you. Oh, but you ask me after class. Yeah, like turn it in, ask me. I'm going to give these ones back with my initials on it, by the way, because this stuff's on the test.
Right.
So I'll hang around. I'm not going to try I may not get through all the stuff today so that I can hang around and help you guys study. But we're going to lecture for a while. Okay, so this chapter is about electrons in atoms and the periodic table. So we have atomic theory, if you remember atomic theory. All right, we have the atom, and there's a nucleus. And so what's in the nucleus? Protons and neutrons, right? I'll just spell it out, actually. And then so that's the nucleus. And then there's electrons that are around it, right? It's a weird looking atom, by the way. Electrons. And then what we're going to talk about today is like, so that's kind of a picture. We think of about atoms. What are atoms' shapes? What are they shaped like? Grapes? Yeah.
Grapes on cluster.
Yeah, it's reasonable. Like grapes in a cluster might be a good reasonable. Like, because you have the little seeds in the middle. This is not the seedless ones, right? The ones with the seeds. Because that would be the nucleus.
Oh, right.
Yeah, right. And then there's that, like the grape stuff. I don't know what to call the grape stuff. It's the grape stuff, right? And that's kind of how we think of atoms. Roughly speaking, that's pretty close to right. The pulp that's around the seeds, those are the electrons. And you're like, think to yourself, okay, let me ask you a question. Survey, think in your head. Electrons are like matter, particles, or they're like light waves.
Yes.
What do you think of electrons as? The answer is yes. Most people think like, oh, it's an electron, it has a mass, it's like a particle. So that's what we're dealing. We're dealing with little, like, more little seeds, right? But it turns out electrons are both. They behave like both. Okay, so we'll talk about that a little bit. But that's kind of like makes your head, when you talk about it too much, your head goes like this. So I'm not going to. There's a video link in here if you want to click on the video link and watch it. That's basically all I say about that, unless you want to ask more questions. But in order to understand light, we have, or electrons in atoms, we have to understand a little bit more about what light is. So I stole some pictures from your book and then I modified them so they actually had information in them. Sorry. So light is a wave. Waves are unusual. They have properties because they don't have mass, right? So what is a, I should say, light wave? All right, so what is a light wave? Well, it's just pure energy. And so when we're thinking about light waves, right, light travels, how fast does light travel at? It's a stupid question. The speed of light. So there's this, light has, you've heard that term before, right? Light speed. Oh, you did say that?
Yeah.
Nice, thank you. So light travels at the speed of light. We give it that, it's got its own symbol, C, and it's 3.00 times 10 to the 8th meters per second. How far is that, right? Well, a football field would be like 10 to the second. So it's like a million football fields. So you can't even imagine that, right? Like you see one football field and how long it takes you to run across a football field. Like if you're the fastest person in the world, it takes around 10 seconds. All right. Light does a million of those in a second. It's just like a huge number. So it's going really fast. But when light is traveling as a wave, right, it's actually energy that's moving. So we think about light waves as fluctuation in energy. And it's part of what's known as the electromagnetic spectrum. So it has both electrical components and magnetic components. And the guy who originally discovered this, his name was Michael Faraday. And he did experiments trying to figure out what the nature of light was. And one of his things, he had this thought that light must have some sort of magnetic feature to it. So he created a magnet that was strong enough that when light passed through a piece of glass, the light turned. He was able to turn the light. Okay, so then you have to think about like when this happened back in the middle 1800s. So he didn't have wires. He couldn't go to Walmart or Amazon and buy a magnet. He had to make his magnet, electromagnet actually. So it's an electromagnet. I don't know if you've ever seen one. You just take a wire and you wrap it around a piece of metal, and when you run a current through it, it makes a magnet out of it. So you can hook it up to a battery. So you can do this at home, get a nail, and you, I don't want to tell you this, wrap, I should do this at home. I haven't done it in ages. You do it with your kids, and then you do it with one, and then you don't do it with the next one because so many years pass, you kind of forget. But you wrap the wire around the nail, and you take like a 9-volt battery, or it doesn't have to be 9-volt, and you connect the ends of the wire to the battery. Now it's going to get hot, so you can't like hold on to it. And then you can touch it to a piece of metal like a paper clip, and it'll be magnetized. It'll be able to pick it up, and then when we take the battery off, it falls. So by passing an electric current through a wire wrapping a piece of metal, you can create a magnet. So he did this, but he didn't have, think about this, he didn't have electricity. He had to make a battery. So he made a battery, he made wires, and he made his magnet. And yeah, so he had to make everything. And when he did that, he also had to make the glass to pass the light through so he could, crazy guy. Yeah, so he was able to turn light. So the idea is this, we think of light as just like brightness, but it actually has both electrical components and magnetic components to it. Okay, so we call it part of the electromagnetic spectrum. You don't need to know the background story, it's good to know that, but just to know that that's, when I say electromagnetic spectrum, I'm talking about light, okay? So it's really the movement of energy, and it doesn't have mass. Okay. It doesn't have mass. So it's not matter, right? There's energy that it turns out, and then there's matter. Light is very light, ha, 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 sorry. Sorry. This is stupid. So light behaves as a wave. This is the way we theorize light as. And when you have light waves, they're going to have something called a wavelength. So the wavelength, we use the symbol lambda. Okay? So that would be one wavelength. A wavelength is the distance from one peak to peak, but really it's the distance between any two repeating parts of the wave. So I could have also said it's from here to here. And that would be lambda as well, okay? It has an amplitude. Depending on how you define it. Simple terms, how big the light wave's amplitude is how bright it is. Okay. The wavelength is related to the color. And the brightness thing, like if you take Chem 1A, will clarify like what it means when it's brighter. It's actually two waves add together, it makes it brighter. If you take Chem 1A. Yeah, no, you're not, don't worry about it. But if you do take Chem 1A with me, then it's in the afternoon, thank goodness. You get sleep in all morning, do your homework in the morning, study for exams in the morning, ask your questions in the morning. Now you can just get the text me at night and hope I respond. Okay. I'll show you something else in a second, but this equation, okay, is the relationship between the frequency, the wavelength, and the speed of light. Okay. Frequency, wavelength, and speed of light. So frequency, let me explain what frequency is. Frequency is the number of waves that pass per second. This symbol here is actually nu. You can just draw a V, it's a Greek letter. Okay. So if you're standing here, right, and light is going past you, the frequency of the light determines how many waves, oscillations go past you in a second. So like when you have I don't know if it says anything on the back of this. Everything has a frequency. Like, I don't think they list the frequencies for these phones. A lot of times it's on the back. Yeah, it's not on there. Like on the back of an electronic device, like you have a cordless phone at home, or you don't have a phone maybe anymore. But if you had a cordless phone at home, it'd be like a 5 gigahertz or 2.4 gigahertz. Giga is 10 to the 12. It's the number of waves. Let's see. No, it's 10 to the 9. It's the number of waves that pass you per second from that phone. So when you pick up like a cell phone or a cordless phone and it says 2.4 gigahertz, it's sending out 2.4 billion waves going past you per second. They're going at the speed of light, right? And going past you that many per second, which is why people worry about them, but I think they're just being paranoid. Okay, so lambda times c, lambda times nu is equal to 3.00 times 10 to the 8 meters per second. This is a constant. It's very fast and it's always the same. That's kind of a lie. I'm just telling you that up front. Yeah. Light slows down a little bit when it goes through matter. That's how we just explain things like diffraction. Anyways, we're just going to call it constant. Everybody's going to tell you it's a constant until you, like in your upper division classes, and say, well, it's actually not a constant. We're like, oh. In space, that's about what it travels. Okay. If this is if the speed of light is a constant, if the wavelength gets longer, what has to happen to the frequency? It has to get lower, right? Lower frequency, as we say. So wavelengths get longer, and they're measured in meters, right? the frequency gets smaller or lower. So they're inversely related to each other. The other thing is to kind of understand, but we're not going to deal with it in this class, is this relationship. This is one of the things a guy named Max Planck came up with. And what he said was the energy of a light wave, like actually a packet of light, the energy of a packet of light, and we'll talk about that more again later, is related to its frequency and a constant. Now this constant is really small. You don't need to know the constant. But what happens to the energy if the frequency goes up? If this number's bigger, what happens to this number? It's going to be bigger, right? So they're proportional to each other. So wavelength and frequency are inversely proportional, and frequency and energy are proportional, right? So you can think about it like if you're standing in the ocean and waves are coming at you, right? If the wavelength is short, there's lots of waves, then there's a lot of energy hitting you. But if the wavelength's long, like the big swells sometimes, right? That's low frequency, low energy. Okay, so lots of waves in a second, that's a lot of energy. Few waves in a second, that's low energy. Okay, so what does this have to do with light? Well, light's a wave, and if you take just white light, like sunlight, right, or a light bulb, like an incandescent light bulb, not fluorescent lights. It turns out fluorescent lights don't look like this. But you take a incandescent, like a regular filament light bulb, and you pass the light, you make a little line out of it by passing it through a slit, and you run that through a prism. What you'll see is a spectrum of colors. Okay? Your eye sees red, right? That's a longer wavelength. You notice how these are longer, right? Longer wavelength. When your eye sees blue, it's actually seeing shorter wavelengths. So you have cones in your eyes and rods that distinguish the colors by how they react to the different wavelengths. They absorb the energy, and that's what creates color in your eye, right? Or what you perceive as color. So, you guys know Roy G. Biv? Who doesn't know Roy G. Biv? Red, orange, yeah. Red, orange, yellow, green, blue. Indigo is like in here somewhere. And then violet, like that. Roy G. Biv. Of course, your slide's black and white, so it's just like gray, 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 gray. It would be just. Sorry. Yeah, so when you hear the term Roy G. Biv, you know, they did it to help us remember. They made this saying, I guess. It represents the colors of the rainbow in order of increasing what? Wavelength is R is the longest wavelength, right? V is the shortest wavelength. So this is the lowest energy. This is the highest energy. So Roy G. Biv is increasing energy. Now, that's shorter wavelength, higher frequency. I'll say shorter lambda and then increasing frequency. All right. Yeah, so increasing energy, shorter wavelengths, increasing frequency. All those things are true at the same time. That's why, like, when you go out in the sun, you put sunscreen on, or you're supposed to, sorry. You go out in the sun, you're supposed to put sun. Why are you supposed to put sunscreen on? What's going to damage you? What do they call? What do they call the light? Ultraviolet, right? Ultraviolet is just the wavelengths of light just beyond, or the frequencies of light just beyond violet. That's why it's called ultraviolet. Violet is purple to me. To me, it's just Roy G, because it's all purple. I don't know. I don't even understand what indigo is. I hate to say that out loud, but I'm supposed to know. All right, so this is again stolen from the book. So we talk about the electromagnetic spectrum, right? See this? This is Roy G. Bibb down here. All right. So which side is high energy? This side, the violet side, is the high energy. So this is in order of red, orange, yellow, green, blue, some color that I don't really know, and violet. Right. This is in the electromagnetic spectrum. This is all we get to see. We get a little tiny fraction of the light that's out there. Right next to violet, that's violet down here, is the ultraviolet. Right. And that has enough energy that it breaks chemical bonds. And this is the reason why it causes skin cancers. It can break up your DNA and cause mutations and stuff like that. Right. On the other side of violet, this is red, right? So violet all the way to red. What's below red? Infra means below red. So these terms, infrared and ultraviolet, these parts of the electromagnetic spectrum, these are parts we can't see. If you're a mosquito, it turns out you can see in the infrared. And that they can actually see when you exhale. Like if you could see in the infrared, you would see clouds around everybody's head because the carbon dioxide that you exhale and the water that you exhale, it absorbs a lot of infrared light. So a mosquito would see you in the dark because it can see in the infrared, and that's how it finds you at night. Like you try to cover your head up because there's a mosquito in your room, and it still manages to like find the one piece of your body because heat is also infrared. It can see the heat radiating from your skin. That doesn't make you paranoid. Now, turns out, just side note, for you people who like biology and flowers, if you take a picture of a flower in the ultraviolet, again, we can't see ultraviolet, but if you take a picture of flowers in the ultraviolet, they have runways on them that the bees can see. Insects can see in the ultraviolet as well. So when a bee is flying around, like we often wondered, like, how does it know to go to the middle? You can literally see lines like pointing towards the middle in the ultraviolet spectrum. It's weird. We can't see any of it. Right. Now, side notes, you got to know this, okay? You don't need to know the exact wavelengths, but I want you to know the order. Lowest, this is lowest energy to highest energy. So here's infrared, ultraviolet. Those are the ones that are easy because they're next to red and next to violet, right? And then there's microwaves. What do we use microwaves for? Food. You heat up your food with a microwave. Turns out water molecules are great at absorbing microwave radiation. And so when they absorb the microwave radiation, they emit heat. And they'll heat up your food. So when you're heating your food up, you're really heating the water up that's in your food. And then there's radio waves. What do we use radio waves for? Radios. So it's radio. These are the longest wavelengths. You'll notice that these wavelengths that they give here in meters, radio waves can be, this is 10 to the 5th meters. It's a 100,000 meter long wave. You can't see it. Too low in energy for your eye to pick up. Then there's, again, radio waves, microwaves, infrared, and then there's ultraviolet, and then there's X-rays. What do we use X-rays for? I love asking questions like this. X-rays, yeah. They mostly go through tissue or blocked by like calcium in your bones, right? And sometimes I'll do images of your intestines and they'll make you drink this nasty thing, which is just a solution of calcium or barium, which absorbs the X-ray radiation, so it makes a picture of your intestines. Okay. And then after that, we have gamma rays. And gamma rays are the highest energy. And these are usually associated with like nuclear reactions. We see a lot of gamma radiation coming from stars. Okay. So radio, microwave, infrared, ultraviolet, X-rays. And visible is that tiny sliver in the middle. Yeah, there's a lot of stuff about that. Okay, so we're gonna take a break. Yeah, we're gonna take a short break. I need to pick up a piece of equipment so I can show you a demo. 10 minutes. Oh, pause the recording. Come on, get on the ball. Pretty good.